right, guys, let's go ahead and pick up by checking the one we just finished. So if we want to take a look at checking, then what we want to do is differentiate our -1/x with respect to x. And what we want to do in this case is kind of reverse the process that we went through before. If we want to differentiate our function, we want to put this back in a negative exponent form. So if we are differentiating, now we can apply the power rule for derivatives. So I can drop my power, multiply that in front. So my negative times -1 gives me a positive. And then if I drop my power, -1 minus 1 gives me a -2. And that's it. So if we put this back into our form, this is really 1/x squared. So what we're looking for on the previous part is, notice what we found was the antiderivative of 1/x squared dx was -1/x. That means when we differentiate -1/x, we should get back 1/x squared. Now, a little bit more terminology. This part, when you're looking at the 1/x squared dx, the 1/x squared is called the integrand. So an antiderivative is the same thing as an indefinite integral. We'll introduce several names for this. Antiderivative, or an indefinite integral. We'll talk about what the indefinite means when we contrast it with a definite integral, but the idea of an integrand kind of pairs with the integral notation or the integral language. So let's take a look at what we have so far. What we know so far, rules for integrals, is the power rule. So the power rule tells me when I'm going to put my n to the negative, or n cannot equal -1 at the top here. So if n is not equal to -1, then our power rule for integrals says we have 1 over n plus 1, x to the n plus 1. Or we could also rewrite this as x to the n plus 1 over n plus 1. Either way. Now, we also have the idea of pulling out constants. And we mentioned this already, but in formal notation, what it means is if you have c times f of x, you can pull your constant out of your integral and essentially ignore it. So, for example, this is what we were utilizing when we said, let's integrate maybe do 2x to the 5th in this example. So when I think about this 2, I'm basically saying ignore it and focus on the x to the 5th. Formally, that means we can actually write it with the 2 on the outside to help us visually separate what's going on. And then that allows us to bring that 2 down and focus on the x to the 5th portion. So power rule says we'll add 1, becomes our new exponent, and we divide by that. So this becomes x over 3, or 1/3, oops, sorry guys, x to the 6th over 3. So we're just simplifying that fraction and then cleaning that guy up. So if we reverse this and differentiate, we should get back our integrand. So quick check. We differentiate x to the 6th over 3. We have 6 times, two parentheses there. So 6 times, we can even pull the 1/3 out. And then we've got x to the 5th. So this gives me my 2. And that matches my integrand. So that's a check. All right, so let's go back and add to our list of rules. What we would like to do is expand upon this power rule, and then we'll go to exponentials. So what we want to do is consider what happens in the -1 case. And we already said that x to the -1 is problematic because of that division by 0 in the power rule. But if you consider this function, x to the -1 is actually a 1 over x. So when we're saying the integral of x to the -1, this is the same thing as the integral of 1 over x dx, rewritten in a different form. So when we're trying to figure out what in the world this is, what we're really asking is, what function can I differentiate to give me 1 over x? I'm going to write that out in long form. Now, it's been a long time since we explored all of our derivative rules, but you may remember, oh yeah, 1 over x was connected to natural law. So if you think about that rule, the derivative of natural log of x is 1 over x. So it turns out that the n equals 1 case, our special case, is related to natural log. It's not related, or it doesn't follow the form of our other power rules. It's kind of a special case. So it turns out that there's a little bit of trouble with just putting natural log. What we actually have to do is include an absolute value, because it turns out if you differentiate the natural log of the absolute value, you also get 1 over x. So here's the rule. This is going to be our third rule. Rule number 3. The integral of 1 over x dx is the natural log of the absolute value plus c. Now, if you just say natural log, I'm not going to be too picky about that, but there is always that absolute value on there. So that's a nice one to have in our back pocket. And then the other case we really want to talk about today is the e to the x, the exponentials. We touched on this in the first part, but exponentials and power rules get confused pretty easily. So let's take a look at a couple antiderivatives or indefinite integrals with our new notation with exponential. So let's say I do the antiderivative or the indefinite integral of e to the x with respect to x. What we're asking is, what function do I differentiate to give me e to the x? And in this case, it's e to the x. We still need our plus c, because we know if we differentiate e to the x plus c plus any constant, we'll just get back e to the x. Okay, so this is actually a nice rule to have in our back pocket. Turns out that in 7.1 and 7.2, for any exponential function, we're going to focus on base e, and we're not going to do like base 2, although those are just in your book. We may see a few in there more as a bonus level if you want to take a look at those in your textbook, but we'll focus on these ones together. So this has to do with rule 4. We're not quite ready to we're not quite ready to write rule 4 out yet. Let's consider one we return to one we considered previously. So if we had e to the 2x dx, and we're integrating, this is saying, tell me the function whose derivative is e to the 2x. Now, we might start by saying, hey, here's my guess. And I'm going to write it in red with a question mark. We might just say, hey, what about e to the 2x plus c? Well, think about if you start and differentiate this guy. We know the derivative of our constant is going to be 0. But if we differentiate e to the 2x, we're going to get e to the 2x, e to the power, times the derivative of the 2x, the derivative of my n. So this gives me 2 e to the 2x. So notice what parts we got right. We got the e to the 2x part right, but we actually don't have the correct constant. So I'm actually going to put an x over it, but it's almost. Okay. what we're missing is something that's going to take care of that 2. In other words, that 2 is really the problem. So if we started with that and we get an extra 2, the way we can handle it is to divide that 2 at the beginning, and then it's going to cancel out. So when you see an extra 2 that doesn't match up, what we could do is 2 different things. We could say, I'm going to guess, I'm going to modify my guess. And if I had an extra constant, I just divide by whatever that constant is. So that if I differentiate now 1/2 e to the 2x, I know my constant's taken care of. I get, ignore my constant, e to the 2x times 2, and that gets taken care of. So this is probably the easiest way to do it. And if we take a look at this one, what this is saying is, hey, that guy worked. So the antiderivative of e to the 2x dx was 1/2 e to the 2x plus c. It turns out in this case, it almost feels a little bit similar to what we saw before, but it's not quite power rule. You're not adding 1, it's the same exponent, but you're dividing by the constant part. Here's what the rule actually looks like. We'll call this rule 4. At least 4 in our list. The exponential rule. It says e to the kx, where k is some constant. It could be positive, it could be negative, it could be rational. Technically, it could be irrational. We're not really going to see many of those. It says you should do 1 over k times e to the kx plus c. So this allows you to quickly do things like integral of e to the 3x, 1/3 e to the 3x. And then you can also introduce some new constants. So for example, let's say I had 5 e to the 2x. Well, here's how I would do it. I would say I'm going to first of all pull out that constant so that I'm thinking about 5 times the integral of e to the 2x with respect to x. And then I'm going to go ahead and do 5 times e to the 2x over 2. You could either pull that 1/2 and find or write it over 2 plus c, which is 5/2 e to the 2x plus c. So we want to get comfortable with these different types. Okay. I'm going to put all the rules back together, and then we have one other part that we want to look at. Power rule. Add 1 and divide by the same power. Constant rule. Pull out your constants. Let's see, we listed the 1 over x rule next. And then our exponential rule. Now, one thing we haven't taken a look at yet is things like polynomials, where we have things added and subtracted. But it turns out that we can handle that pretty easily. It turns out if you have 2 functions that are added together as an integral, so like I should probably say f of x plus g of x here. Turns out that you can go ahead and split that up into 2 pieces. Integrate one function, integrate the other, and sandwich them together. So let me do a quick example of what rule number 5 looks like, and then we'll stop this video and do a part 3 on some initial value problems. So really quickly on this one, let's say you were integrating something like x cubed minus 5x plus 1, a polynomial. Well, individually, we know how to handle these. Maybe the 1 is a little bit different, but this is actually saying I can break it up and integrate the x cubed piece. I'm going to go ahead and integrate the 5x piece, pull my subtraction out here, and then I can go ahead and integrate the 1. Okay, so don't lose that plus 1 for your integral of the 1, because notice first piece is x to the 4. I don't need plus c 3 times. I can go ahead and condense that into 1 constant. Then I'm also going to go ahead and pull this 5 out. So if I do, if I were to have written it minus 5 integral of x dx, that would have been a little better. But I'm going to go ahead and think about this one as having an exponent of 1. So when you write it like that, you can see that we're going to have minus 5 x squared over 2. So we should have power 2 on that one. And then additionally on this guy, what we're really asking is, what do I integrate? Or excuse me, the integral of 1 is asking me, what can I differentiate to give me back 1? And if you think about what you differentiate to get 1, it's just x. You differentiate x, you get 1. Think about it like 1x. Another way to think about this is it's really like x to the 0 when you don't see an x. This x to the 0 is also another way to say 1. So you can think about applying your power rule here, but I like to remember anytime you're just integrating 1, or let's say if you integrate 2, well, that's 2x plus c. If you integrated 3, 3x plus c. If you integrate 1, 1x plus c. Okay, so clean it up a little bit. And this is the idea of breaking it apart. So I'm going to go ahead and stop this part of the video now. Actually, need to plug my computer up. And I'm going to record another part showing you how to handle one additional type that you're going to see in this section. All right, guys, so I'm going to stop this for now.